In August 2025, humanity may have watched a world appear and then slip back into darkness. Not metaphorically, not symbolically, literally. 4 light-years away, around the nearest sun-like star to our own, something showed up in our most powerful telescope. And then, weeks later, it was gone. No explosion, no warning, no trace. And if what astronomers saw was real, then we just witnessed one of the strangest events in modern astronomy. Because planets don't just disappear. The James Webb Space Telescope was never designed for drama. It was built for patience, for silence, for the faint glow of ancient galaxies whose light began its journey before Earth even had continents. Webb stares into the infrared universe, where heat lingers and whispers carry across cosmic time. But in late spring of 2025, Webb wasn't looking backward. It was looking next door, at Alpha Centauri A. In a star so close that if the Milky Way were the size of North America, Alpha Centauri would sit on the same city block as our sun. It's bright, familiar, visible to the naked eye from the southern hemisphere. And for decades, it refused to answer one simple question. Does it have planets? Thousands of exoplanets have been discovered around distant stars. Gas giants, lava worlds, ocean candidates, systems stranger than science fiction. Yes, we have found planets orbiting suns hundreds of light years away, but the system closest to us remains stubbornly silent. Until Webb looked. Alpha Centauri A is almost a twin of our sun, slightly larger, slightly brighter, billions of years old. If there were ever going to be another solar system we could realistically explore, not in fantasy but in physics, this would be it. But there's a problem. Alpha Centauri isn't alone. But it's locked in a gravitational dance with Alpha Centauri B, the 2 stars circling each other in an 80-year orbital ballet. Their gravity stirs space around them like competing tides, and that makes planet hunting brutally difficult. Looking for a planet next to Alpha Centauri A is like trying to spot a firefly next to a searchlight, while another searchlight sweeps past every few decades. Most exoplanets are found indirectly. You measure a star's wobble. Yet you watch for a tiny dip in brightness when a planet crosses in front of it. But Alpha Centauri's binary motion complicates everything. The wobble from its stellar partner masks the subtle tug of planets. So astronomers turned to something far more difficult: direct imaging, actually seeing the planet. And that's where Webb changed the game. Webb sees heat. Even a cold gas giant, one far from its star, emits faint infrared radiation, not reflected light, not sparkle, like warmth. Webb carries a coronagraph, a device that blocks starlight, creating an artificial eclipse inside the telescope. It's like holding up your hand to block the sun so you can see what's beside it. But this isn't easy. Alpha Centauri is the 3rd brightest star in Earth's night sky. Too bright, and Webb's detectors risk saturation. Too misaligned by even a fraction of an arcsecond, and starlight leaks through, flooding the image. Yeah, so the observing team did something meticulous. Webb first locked onto a nearby reference star. Then it performed a blind offset, shifting position with surgical precision to place Alpha Centauri A exactly behind the coronagraph mask. If they were off by the width of a human hair seen from kilometers away, the observation would fail. They rotated the telescope between exposures. They captured multiple infrared wavelengths. They gathered hours of data. And when the raw images came down, they looked like chaos. Diffraction spikes, scattered glare, interference patterns from the companion star. To an untrained eye, it was noise. But astronomy isn't about first impressions. It's about subtraction. Layer by layer, the team removed instrument artifacts. They modeled how starlight diffracts around the coronagraph. They subtracted reference star patterns. They filtered out correlated noise. They rotated and combined images from different telescope orientations to distinguish real celestial objects from internal reflections. And then something remained, a faint point of light, steady, consistent across independent exposures, located about 1.5 arcseconds from Alpha Centauri A. From Earth, that separation corresponds to roughly 2 to 3 astronomical units, about the distance between the Sun and the asteroid belt. It wasn't bright. In fact, and it was roughly 10,000 times dimmer than the star beside it, but it was statistically strong, 5 sigma. In physics, that's discovery territory. The probability of it being random noise? Less than 1 in a million. They labeled it cautiously, S1. Not planet, not yet. Just Source 1. But its infrared brightness told a story. Based on its thermal emission, S1 appeared to be warm, between 200 and 300 Kelvin, cold by Earth standards. But exactly what you'd expect for a mature gas giant orbiting a sun-like star at that distance. Its estimated mass? Roughly Saturn's. 90-plus Earth masses of hydrogen and helium. A world with no surface. A planet that, if confirmed, would be the closest directly imaged exoplanet in history. The nearest world beyond our solar system that we could actually see. 4 light-years away. Close enough that a spacecraft traveling at a fraction of light speed could reach it in a few decades. Close enough that for the first time in history, interstellar exploration felt less like fantasy, and more like engineering. The discovery spread quickly. Headlines exploded. Planet found around Alpha Centauri. Our nearest stellar neighbor has a gas giant. Webb makes historic discovery. Space agencies quietly took notice. If Alpha Centauri A has one planet, it likely has more. Gas giants rarely form alone, and inside that system's habitable zone, the region where temperatures allow liquid water, there could be rocky worlds, moons, oceans, possibilities. For a brief moment, humanity felt like it had glimpsed its future destination. But then, 2 months later, they looked again. In October 2025, a different team requested follow-up observations. If S1 were a planet, it should have moved slightly along its orbit. Not vanished, not exploded, just shifted position predictably, following the laws laid down by Kepler 4 centuries ago. Webb pointed back at Alpha Centauri A. Same instruments, same coronagraph, same wavelengths. The data came down, the processing began, the subtraction, the modeling, the noise filtering. And when they examined the location where S1 should have been, there was nothing. No faint warmth, no point source, no 5 sigma signal. Just empty space. They widened the search. Maybe orbital motion moved it farther than expected. Still nothing. They reprocessed the data. Different thresholds, different reduction pipelines, independent analysts. Same result. S1 was gone. Now planets can move. They can hide behind stars during occultation. They can dim slightly due to atmospheric variation. But they do not simply disappear in 2 months, especially not a Saturn mass giant. Such an object weighs nearly 6 times 10 to the power of 26 kilograms. That's 95 Earth's worth of gravity holding hydrogen and helium in a sphere larger than 100,000 kilometers across. To destroy something like that would require a catastrophic collision, and such an event would leave debris glowing for years. There was no debris, no infrared flare, no aftermath. Alpha Centauri. A looked perfectly ordinary, quiet, middle-aged, unbothered. So the question emerged, spreading across the astronomical community like a shockwave. What did Webb actually see? Was S1 an illusion, an artifact cleverly masquerading as a planet? Or had we just witnessed something no one had ever observed before? A world that flickers, a world that hides, a world that steps briefly into view, and then slips back behind the glare of its star. Because here's the unsettling part. In the weeks that followed, more observations were attempted. And occasionally, faint hints appeared again. Not strong, not consistent, but enough to divide astronomers into camps. Some said it was noise. Others said it was real, and behaving in a way we didn't yet understand. And suddenly, the closest star system to Earth became the site of one of the most puzzling mysteries in modern astronomy. A potential planet, detected at discovery-level confidence, confirmed across multiple exposures, announced to the world, and then gone. If S1 was a false positive, it would be embarrassing, but explainable. If it was real and simply hidden by orbital geometry, it would be extraordinary. But if it was real and genuinely variable, then we may have stumbled onto something new, because planets aren't supposed to flicker on and off like broken light bulbs. And yet, in the glare of Alpha Centauri A, that's exactly what it looked like. A world, appearing, vanishing, waiting. And somewhere 4 light-years away, that star continues to shine, indifferent to our confusion. Because the universe doesn't owe us clarity, only evidence. And in 2025, the evidence raised a question that still hasn't been answered. Did we really see a planet orbiting our nearest stellar neighbor? Or did we just witness the most convincing phantom ever produced by modern astronomy? Either way, The story was only beginning. Before a planet can disappear, you have to understand the star it's hiding behind. Alpha Centauri is not mysterious in the way distant stars are mysterious. It doesn't flicker at the edge of visibility. It doesn't require a powerful telescope to see. On a clear night in Australia, South Africa, or parts of South America, you can step outside and look up. And there it is, bright, steady, almost ordinary. And yet that point of light is not one star. It's a system. A gravitational machine that has been running for billions of years. Alpha Centauri A and Alpha Centauri B orbit each other in a slow, elegant dance that takes roughly 80 years to complete. They approach as close as 11 times the Earth-Sun distance. Then they drift apart to nearly 36 times that distance, back and forth, over and over, for billions of years. Alpha Centauri A is slightly more massive than our Sun, hotter, brighter, a near-solar twin. And Alpha Centauri B is smaller, about 85% the Sun's mass, glowing a bit more orange. And then, far beyond them, there's Proxima Centauri, a dim red dwarf orbiting the pair at an enormous distance. Proxima already has confirmed planets. We know that much. But Proxima is not the star humanity dreams about visiting. Alpha Centauri A is, because it's the closest sun-like star in existence. If Earth had a twin orbiting another sun, this is where we would expect to find it, which makes the silence of that system unsettling. Planet formation is messy, but it follows patterns. Stars form from collapsing clouds of gas and dust. Around newborn stars, disks of leftover material spin like cosmic pottery wheels. Within those disks, particles collide, stick together, grow. Pebbles become boulders. Boulders become mountain-sized bodies. Eventually, gravity takes over. Worlds are born. In our solar system, and this process produced rocky inner planets, gas giants farther out, icy bodies beyond that. So if Alpha Centauri A formed from similar material, and it almost certainly did, why wouldn't it have planets? The answer may lie in the binary. When two stars orbit each other closely, their gravity disrupts the calm conditions required for planet formation. Imagine trying to form delicate rings in water while someone keeps stirring the bowl. Yet computer simulations once suggested that binary systems like Alpha Centauri might struggle to build stable planetary systems, at least within certain distances. But later studies complicated that picture. They showed that stable zones do exist. Regions within roughly 3 astronomical units of Alpha Centauri A where planets could orbit safely for billions of years without being torn apart by Alpha Centauri B's gravity. And here's the key detail. Yet the object S1, the vanishing planet, appeared exactly within that stable zone. Not too far, not too close. Right where theory says a gas giant could survive. That's what made the August detection so compelling. It wasn't random. It fit. But fitting theory and surviving observation are two very different things. Alpha Centauri presents another challenge beyond gravity. It moves fast. It's because it's so close to Earth, just over 4.3 light-years away. Its motion across our sky is measurable year to year. It shifts position relative to distant background stars, and that motion must be calculated with extreme precision when pointing a telescope like Webb. A small error doesn't just blur the image, it ruins it. Add to that the brightness. Alpha Centauri is the third brightest star visible in Earth's night sky. Webb's detectors are designed to capture faint heat from the early universe. Point them at something this bright, and you risk flooding the sensor. Even with a coronagraph, you can't block all the starlight. Some leaks around the mask, some diffracts through optical edges. It creates a halo of scattered light across the image. And inside that halo, astronomers are searching for a point 10,000 times dimmer than the star. It's like searching for a match flame next to a lighthouse. But Webb had one advantage no previous telescope possessed: infrared sensitivity at extraordinary precision. Planets, especially mature gas giants, glow faintly in infrared, not because they're hot like stars, but because they retain residual heat from formation and absorb energy from their star. At wavelengths around 10 to 20 micrometers, a Saturn-like world emits detectable radiation. That's where Webb's MIRI instrument operates, mid-infrared. Cooler wavelengths, a place where stars begin to dim slightly and planets become more visible by comparison. It's not an easy task, but it's possible. And in August 2025, Webb proved that possibility. But what made Alpha Centauri special wasn't just its proximity. It was what it represents. For decades, scientists and engineers have studied interstellar travel not as fantasy, but as engineering challenges. A breakthrough starshot, proposed in 2016, envisions sending gram-scale spacecraft propelled by Earth-based lasers to 20% the speed of light. At that velocity, a probe could reach Alpha Centauri in about 20 years. 20 years. Not centuries. Not millennia. A human lifetime. But here's the catch. You don't send probes into the void blindly. You need targets. You need coordinates. You need to know what's waiting there. If Alpha Centauri A has a Saturn mass gas giant at roughly 2 astronomical units, that tells us something profound. It means the system formed large planets. And where there are gas giants, there are often smaller rocky planets closer in. Maybe even in the habitable zone. A habitable zone around Alpha Centauri A lies roughly between 0.7 and 1.3 astronomical units. Not too different from our own system. A rocky world in that band could, in theory, host oceans, atmospheres, clouds, life. The August detection didn't just suggest a planet. It suggested the possibility of an entire system, a destination. And that's why the disappearance felt so destabilizing. Because if S1 was real, then the nearest sun-like star in the universe is not empty. And if it wasn't real, then we are still blind to what may be orbiting right next door. There's another reason the mystery runs deeper. Alpha Centauri has fooled us before. In 2012, astronomers announced the discovery of an Earth-mass planet around Alpha Centauri B. Excitement surged. A rocky world around our nearest stellar neighbor. But later analysis revealed the signal was likely noise buried in stellar activity. The planet was quietly withdrawn. Then in 2019, ground-based observations hinted at a faint object near Alpha Centauri A. They labeled it C1. It was tentative, weak, never confirmed. And then came Webb's S1 in 2025. Stronger, cleaner, statistically robust, until it vanished. If C1 and S1 are unrelated, then Alpha Centauri has produced multiple illusions. But if they are the same object, then we may have been watching the same world move along an eccentric orbit for years, appearing briefly when geometry favors us, disappearing when glare swallows it. Which brings us to the deeper question. What if the problem isn't that Alpha Centauri lacks planets? What if the problem is that our instruments are only barely capable of seeing them? We may not be observing absence. We may be observing the limits of contrast. Direct imaging of exoplanets sits at the edge of physics. The contrast ratio between a star and a planet is enormous. In visible light, a sun-like star is roughly 1 billion times brighter than an Earth-like planet. In infrared, that ratio drops, but it's still extreme. Yet coronagraphs suppress starlight by factors of thousands to millions, but they create blind spots, regions close to the star where residual glare overwhelms faint signals. If a planet's orbit carries it through those regions, it can temporarily disappear, not because it's gone, but because we cannot separate it from the light of its star. This is not science fiction, it's geometry, and that possibility changed everything. Because if S1 followed a highly elliptical orbit, it could have been near its farthest point from the star in August 2025, making it visible. Then, by October, it may have moved inward, crossing into a region where Webb simply cannot detect it. Which would mean the disappearance wasn't destruction, it was concealment. And that's a very different story, but we weren't there yet. At the time of the October non-detection, the astronomical community was divided. Some argued the August detection must have been a false positive. After all, extraordinary claims require extraordinary evidence. Others pointed out that 5 sigma detections are rarely statistical flukes. And then there were those who saw something even more interesting, because in a few of the later observations, faint hints reappeared, not strong enough to declare confirmation, not consistent enough to declare noise, just enough to make everyone uncomfortable. The star we thought we knew, the system we assumed we understood, had become unpredictable, and unpredictability in astronomy is rare. Stars follow physics, planets follow orbits, noise follows statistics. But Alpha Centauri A was giving us something messier, something that flickered. And the only way to resolve it was not debate, not theory, but time. Because if S1 was real, it would come back. Orbit is destiny. And in the next segment, we'll explore every possible way a planet could disappear, and why almost none of them make sense. Planets don't vanish. They don't flicker like faulty light bulbs. They don't blink in and out of existence depending on who's looking. At least, they're not supposed to. So when S1 disappeared in October 2025, astronomers did what scientists always do when reality stops cooperating. They made a list. Every possible explanation, no matter how boring, no matter how exotic. And then they started eliminating them one by one. Hypothesis 1. It was never there. The simplest answer is often the correct one. Maybe S1 was never a planet. Maybe it was noise, an instrumental artifact, a phantom created by light scattering inside Webb's optics. It wouldn't be the first time astronomy has been fooled by its own tools. In the early days of exoplanet hunting, multiple discoveries were later retracted when stellar activity mimicked planetary signals. In 2012, a claimed Earth mass planet around Alpha Centauri b evaporated under reanalysis. Signals can lie, statistics can mislead, even 5 sigma can hide systematics. But S1 wasn't a single spike in one dataset. It appeared across multiple independent exposures, different telescope orientations, different calibration steps. If it were an internal reflection or detector glitch, it would rotate with the telescope. It didn't. If it were random noise, it wouldn't consistently sit at the same location relative to the star. It did. False positives happen. But this one would have required a remarkably disciplined illusion, a perfect impersonation of a planet. Possible? Yes. Likely? That's where the argument began. Hypothesis 2. Orbital geometry planets move. That's their job. Given S1's apparent distance, roughly 2.7 astronomical units, Kepler's laws tell us something important. A world that far from a sun-like star would orbit roughly every 3 to 4 years. That means in 2 months, it would travel only a small fraction of its orbit. A subtle shift, not a disappearance. Unless the orbit was nearly edge-on from our perspective. If the planet crossed directly behind Alpha Centauri A during October's observations, as it would be swallowed by the star's glare, invisible, still there, just hidden. This phenomenon is common in our own solar system. Venus disappears during superior conjunction. Mars vanishes behind the sun periodically. Even spacecraft on Mars go silent when the sun blocks radio signals. But the math didn't cooperate. For S1 to move from clearly visible in August to completely hidden in October, the orbital alignment would need to be exquisitely precise, almost perfectly edge-on. And randomly oriented orbits rarely line up that neatly. Not impossible, but improbably convenient. Hypothesis 3. Catastrophe. What if something destroyed it? A collision. A violent encounter with another massive body. Gas giants can collide. Simulations of young planetary systems show chaos in the early days. Planets migrate. Orbits cross. Worlds smash together. But Alpha Centauri A is billions of years old. A mature system. Stable. Major planet-planet collisions at that age are astronomically rare. And more importantly, they leave fingerprints. If 2 Saturn mass worlds collided, the energy release would be staggering. The debris would glow in infrared for years. Hot gas, expanding clouds, a luminous scar in the system. Webb would have seen it instantly. There was no scar, no excess emission, no aftermath. If S1 died, it did so without leaving a body. And physics doesn't allow that. Hypothesis 4. Dust space isn't empty. Even in mature systems, leftover debris, dust, rocks, icy fragments, can form belts and rings. If S1 passed through a dense clump of dust, that material could absorb or scatter its infrared light, temporarily dimming it. This happens in young systems with thick debris disks. It even happens in ours on smaller scales. When comet Shoemaker-Levy 9 slammed into Jupiter in 1994, it left dark scars visible for months. Dust changes how planets look, but there's a problem. Alpha Centauri A does not show strong evidence of a dense debris disk. A dust cloud thick enough to hide a Saturn mass planet would glow brightly in infrared itself. Webb would detect that glow easily. It didn't. And dust belts don't drift unpredictably in weeks. They're stable over thousands of years. Now, for S1 to vanish precisely during a 2-month observation gap would require stunningly bad luck, or something else entirely. Hypothesis 5. Atmospheric blackout. This is where things get interesting. Gas giants are not static spheres. They are dynamic, violent weather machines. Jupiter's atmosphere roils with storms larger than Earth. Saturn unleashes planet-wide tempests roughly every 30 years. Neptune's massive dark spots appear and disappear within a few seasons. Entire hemispheres can brighten or dim depending on storm activity. Cloud layers shift. High-altitude hazes thicken. If S1 experienced a dramatic atmospheric transformation between August and October, its infrared brightness could drop. Maybe not by 10%, but by 50% or more. Imagine a global haze layer forming in the upper atmosphere, tiny particles blocking outgoing infrared radiation. The planet would still be there, still orbiting, but effectively camouflaged. This scenario doesn't violate physics. It's extreme, but not impossible. And it would explain something even stranger that happened next. Because in December 2025, Webb looked again. And this time, something flickered back. Not the strong 5 sigma signal from August. Something weaker, dimmer, barely above noise. Some exposures showed it, others didn't. It was as if the planet were pulsing. On, off, on again, then gone. Brightness variations by factors of 3 or more. Over days. No known gas giant behaves that way. Rotation-induced changes cause subtle brightness swings. Storms create gradual shifts. But nothing in our solar system flickers erratically like that. The signal was too unstable to ignore, and too inconsistent to trust, which led to the most uncomfortable possibility of all. Hypothesis 6. We are at the edge. What if the mystery isn't astrophysical at all? What if it's technological? Direct imaging operates at extreme contrast limits. We are subtracting one of the brightest stars in the sky from itself, mathematically, hoping something faint remains. Tiny imperfections in calibration can create ghost signals. Minute shifts in alignment can erase real ones. We are trying to see something that is almost but not quite below our detection threshold. When you work at that edge, the universe doesn't behave cleanly. Signals drift in and out of significance. Different reduction pipelines yield different results. The same dataset analyzed 2 ways can produce slightly different answers. In this regime, detected and not detected are separated by razor-thin margins, and S1 may live exactly on that razor. Not a stable, glowing world, not a phantom, but something perched at the limit of human capability. Visible only when conditions are perfect. Invisible when they aren't. By early 2026, the astronomical community was fractured into 3 camps: the skeptics, the believers, and the cautious. The skeptics argued the original detection was a systematic artifact, a rare but instructive false positive. The believers insisted the consistency across orientations proved something real was there. The cautious admitted something might exist, but perhaps not a conventional planet, a dusty substellar object, an eccentric wanderer, a structure we don't yet categorize. And hovering over all of it was a simple, stubborn fact. Planets do not flicker, not like this. Not on timescales of days. If S1 was real, it was behaving in a way no gas giant ever had. If it wasn't real, then Webb, the most advanced telescope ever built, had been fooled by its own brilliance. And either conclusion was unsettling. Because one suggests nature is stranger than we thought, and the other suggests we are less capable than we believed, which leaves one final path to explore. What if the orbit itself is the key? What if S1 isn't vanishing, but diving? Because if the orbit is wildly eccentric, stretched into an elongated ellipse, then the planet's distance from its star changes dramatically over time. At its farthest point, it's visible. At its closest, it's swallowed by glare. And if that's true, then we can predict when it will reappear. And predictions are where mysteries become science. In the next segment, we'll explore the orbit that shouldn't exist, and why 2026 may be the year this planet either proves itself or vanishes forever. If S1 was noise, the story ends quietly. If S1 was destroyed, we would have seen the aftermath. If S1 was hidden by dust, we would detect the dust. But if S1 was moving along a highly eccentric orbit, then everything changes. Because eccentric orbits don't just shift position, they change visibility dramatically. Most planets in our solar system follow nearly circular paths. Earth's orbit is only slightly elliptical, Jupiter's too. Their distances from the Sun vary only modestly over a year, but eccentric orbits can be extreme. Comets in our system swing from the outer darkness to scorchingly close solar passes. Some exoplanets we've discovered follow wildly elongated paths, diving toward their stars, then arcing back out into deep space. If S1 follows such a path, then August 2025 might have caught it near Apastron, the farthest point from Alpha Centauri A. At that distance, separation from the star is greatest. Contrast improves. The coronagraph can isolate it. But as the planet moves inward toward periastron, its closest approach, it slips deeper into the star's glare, and there is a region near every star that telescopes simply cannot probe, a blind zone, too close to the light. If S1 crossed into that zone between August and October, it wouldn't need to vanish physically. It would only need to cross an invisible boundary of detectability, and that boundary is not a line in space, it's a limitation of optics. And to test this idea, astronomers ran orbital simulations. They input the August detection coordinates. They modeled possible ellipses consistent with that position. They varied inclination angles, eccentricities, orbital periods, thousands of simulations. Most orbits didn't work. Too circular, too slow, too misaligned. But a narrow family of solutions did. High eccentricity values above 0.6. That means the orbit is stretched dramatically. At Apastron, S1 could sit comfortably at 2.7 astronomical units. But at periastron, it could dive inward to less than 1 astronomical unit. That's a huge shift. And in that inner region, Webb's coronagraph sensitivity drops sharply. The star overwhelms faint infrared signals. In other words, S1 wouldn't disappear. It would be outshined. Now here's where the story deepens. In 2019, before Webb ever launched, ground-based observations with the Very Large Telescope in Chile reported a faint candidate near Alpha Centauri A. They labeled it C1. It was tentative, weak, never confirmed, but its projected separation was not inconsistent with where S1 would be if following one of these eccentric models. At the time, C1 was dismissed as likely noise, too faint, too uncertain. But if C1 and S1 are the same object, then we've seen it before. Just not clearly enough to believe it. That possibility electrified the orbital modeling teams. Because if an eccentric solution connects C1 in 2019 and S1 in 2025, then we can predict where the planet should be next, and prediction is power. Let's imagine the most extreme viable orbit. Period, about 3.5 years. Eccentricity, 0.65. Inclination, moderately tilted from our line of sight. Under this model, 2019, near periastron. A faint and buried in glare, C1, 2025 August, near Apastron, brightest and most separated, S1, 2025 October, diving inward, slipping below detectability, late 2026, emerging outward again. If this is correct, then sometime in 2026 or early 2027, S1 should reappear. Not faintly, not marginally, but clearly. That prediction reframes the entire mystery. It transforms it from chaos to countdown. But there's a complication. So highly eccentric gas giant orbits around binary stars are not common. Gravitational interactions with Alpha Centauri b would tend to destabilize extreme ellipses over time. Simulations show that long-term stability exists primarily for more circular orbits within about 3 astronomical units. So if S1 truly has an eccentricity above 0.6, something must have placed it there. Perhaps a past gravitational interaction, perhaps an unseen companion. It was perhaps an early scattering event billions of years ago that left it in a stretched but stable configuration. That would make S1 not just a nearby gas giant, but a dynamically exotic one, a survivor of early chaos, a world that swings between extremes, which could also explain something else. Temperature variation. When a planet follows an eccentric orbit, its received stellar energy changes drastically over a single year. At Apastron, it cools. At periastron, and it heats rapidly. If SE1 dives inward dramatically, its upper atmosphere could respond. Cloud layers evaporating, haze forming, infrared emission fluctuating. Sudden changes in brightness might not be random noise. They might be orbital weather. We've never directly observed a gas giant 4 light-years away undergoing such transitions, but theory allows it. And if Webb happened to observe S1 during a dynamic phase, when it was heating rapidly, its infrared signature might shift in complex ways. That could explain the December 2025 flickers. Not destruction, not illusion, but evolution. Still, skeptics remained unconvinced, because orbital models can be tuned to fit many possibilities. When you have one strong detection and several weak ones, it's dangerously easy to build a narrative around them. Which prediction is only meaningful if it succeeds. If 2026 passes without reappearance, eccentricity becomes wishful thinking. But if S1 returns on schedule, then the vanishing planet was never gone. It was hiding in motion. This is the moment where astronomy turns into suspense, because unlike collisions or dust clouds, eccentric orbits offer something rare, a testable future. You don't need arguments, you don't need Twitter debates, you need time. And either the planet comes back or it doesn't, and that binary outcome will determine whether August 2025 was a breakthrough, a false alarm, or the first glimpse of a world that refuses to stay still. There's something profoundly human about this phase of the story. We discovered something, we doubted it, we argued about it, now we wait. Waiting is uncomfortable, especially when the object in question is orbiting the nearest sun-like star in existence. Because if S1 is real, then Alpha Centauri A is not empty. It has architecture, it has structure, and if there is one gas giant, there may be smaller inner worlds, rocky planets, moons, possibilities. But if S1 is an artifact, then we are still blind, still searching, still uncertain about what lies just 4 light-years away. And so 2026 became the pivot year. Observation proposals were submitted, Webb time requested. There was ground-based, extremely large telescopes preparing adaptive optics campaigns, independent teams planning spectroscopy, not to debate the past, but to test the orbit. Because if S1 reappears at the predicted position, if it moves exactly where Kepler says it should, then not only does the planet exist, its disappearance becomes the most beautiful demonstration of orbital mechanics ever witnessed in exoplanet science, a world that vanished only because it moved, and a ghost revealed as geometry. But if it doesn't come back, then we're forced to confront a different conclusion, that we glimpsed something at the very edge of our instruments, something that may not exist at all. In the final segment, we'll explore what this mystery means for humanity's future, because Alpha Centauri isn't just another star, it's our nearest doorway to the galaxy, and whether S1 is real or not, and the implications reach far beyond one flickering point of light. The question is no longer just, did a planet disappear? It's, how close are we to touching another solar system, and whether we're ready for what we might find there. There is something almost poetic about this, humanity's nearest stellar neighbor, 4 light-years away, a destination we've whispered about for generations. And now, in the most advanced era of astronomy we've ever known, today we are arguing over a faint dot of heat beside it, not because we lack intelligence, not because we lack ambition, but because we are standing at the edge of what is technically possible. Alpha Centauri is not just another entry in a star catalog. It is the first place beyond our solar system that we could realistically reach. Not in myth, not in fantasy, but in engineering. Yeah, projects like Breakthrough Starshot have already outlined a radical plan. Gram-scale spacecraft, laser-propelled to 20% the speed of light. At that speed, a probe could cross the 4.3 light-year gap in about 20 years. 20. That's shorter than the time between the Voyager launches and today. If we launch in the 2040s, images could arrive before the end of the century. But here's the uncomfortable truth. You don't launch toward emptiness, you launch toward something. You need a target, coordinates, a reason. If S1 is real, then Alpha Centauri A has structure, a gravitational architecture. And where there is a gas giant, there are usually inner worlds. In our solar system, Jupiter didn't form alone. Saturn followed. Then Uranus, then Neptune. Closer in, rocky planets. If that pattern repeats at Alpha Centauri A, then inside its habitable zone could orbit a rocky world. Maybe dry and barren, maybe cloud-covered. Oh, maybe ocean-bearing. We don't know. But S1, if confirmed, would be the first solid piece of that puzzle. And then there are moons. Saturn has over 80. Some are tiny captured rocks, but others are worlds in their own right. Titan, with lakes of liquid methane and a thick nitrogen atmosphere. Enceladus, with a subsurface ocean spraying water into space. A Saturn-mass planet around Alpha Centauri A could host similar moons. Potentially habitable environments orbiting a gas giant instead of a star. Worlds warmed by tidal heating, protected by thick atmospheres. The closest exomoon we could ever study, 4 light-years away, if S1 is real. But what if it isn't? What if August 2025 becomes a cautionary tale, an example of what happens when we push instruments to their limits? That too matters, because knowing the limits of detection is just as important as making discoveries. And as the first exoplanet claims in the 1980s were wrong, later they were corrected. The first gravitational wave detection was doubted, until confirmed. Science advances not because we never err, but because we test, relentlessly. If S1 turns out to be a false positive, it will refine our methods, improve our calibration, strengthen future detections, and when we finally image a confirmed planet around Alpha Centauri A, it will be unquestionable. There is another layer to this story. 50 years ago, a discovery like this would have unfolded quietly in journals. Arguments exchanged in conferences, debates contained within academia. But today, astronomy unfolds in public. Announcements trend on social media. YouTube channels analyze data before peer review completes. Every twist becomes global news. The vanishing planet wasn't just a scientific anomaly, it was a spectacle. And that transparency changes how science feels. It exposes uncertainty, it reveals disagreement, it makes the process visible, and sometimes messy. But that messiness is not weakness, it's honesty. You are watching science happen in real time. Discovery, doubt, verification, revision. That is how knowledge is built. As of now, the story remains unfinished. Observations continue. Teams prepare for the predicted reappearance window. Simulations are refined, data pipelines adjusted, new telescopes are rising from desert floors, 30-meter mirrors, 40-meter giants, adaptive optics so precise they can cancel atmospheric turbulence in real time. Within the next decade, our ability to image nearby exoplanets will increase dramatically. If something is orbiting Alpha Centauri A, we will find it, not eventually, soon. But the deeper meaning of this mystery isn't technical, it's existential. And yet for thousands of years, humanity looked at the stars and wondered if they had worlds. A century ago, we didn't know the answer. 30 years ago, we confirmed the first exoplanet around a sun-like star. Today, we've cataloged thousands. Gas giants, super-Earths, water world candidates. But none of them were within reach. Not truly. They were too far. Dozens, hundreds, thousands of light years away. Alpha Centauri changes that equation. And it is close enough that interstellar exploration shifts from mythology to engineering challenge. And that shift is profound. Because once a destination becomes reachable, even theoretically, it stops being abstract. It becomes part of our future. Whether S1 is real or not, we are no longer asking if planets exist around other stars. We are asking which planets orbit the star next door. That is a different level of curiosity, more focused, more urgent, and more personal. If Alpha Centauri A hosts planets, they are the first exoplanets humanity might one day see up close. The first alien horizons our descendants could photograph. The first sunrise under a foreign sun that might be witnessed by human-built machines. And that possibility is powerful enough to justify every hour Webb spends staring into glare. There is a philosophical edge to all this. When does something become a discovery? And is it when a signal crosses 5 sigma? Is it when multiple teams confirm it? Or is it when time fails to erase it? S1 sits in that liminal space. Detected, disputed, not yet confirmed, not yet dismissed. Existing somewhere between fact and possibility. That ambiguity is uncomfortable. We prefer certainty, but frontier science rarely offers it. Instead, it offers tension. And tension is where breakthroughs live. Imagine two futures. In the first, 2026 arrives. Webb observes Alpha Centauri A again. At the predicted position, a clear, steady infrared source appears, stronger than December, moving exactly where orbital mechanics said it would. The flickering resolves into pattern, the eccentric orbit confirmed, the vanishing explained, headlines return. But this time with confidence. The nearest sun-like star has a gas giant. And the search for inner rocky worlds accelerates. In the second future, 2026 passes quietly. No reappearance, no signal. Upper limits grow stricter. S1 fades into statistical anomaly, a lesson in instrumental limits, and Alpha Centauri remains an open question, empty or simply undetected. Both futures teach us something, only one changes our trajectory. But here is what does not change. We are going to keep looking. Because Alpha Centauri is not optional, it is inevitable. The nearest star system demands exploration. If not by crude ships, then by photons. If not by rockets, then by telescopes. We are already there, in a sense. Our instruments orbit far beyond the moon. They unfold golden mirrors. They block starlight artificially. They subtract noise mathematically. They hunt for warmth in darkness. That is exploration, even before propulsion. The vanishing planet, whether real or phantom, marks a threshold moment. It shows that we are capable of detecting worlds at the edge of visibility around the star next door. That capability did not exist a decade ago. It exists now, and it will only improve. In your lifetime, we will likely image a rocky planet around a nearby sun-like star. We will analyze its atmosphere, search for oxygen, methane, biosignatures. We may detect something unexpected, a chemical imbalance hinting at life. And when that happens, yet the debate over S1 will feel like a prologue, because the true revolution will be confirmation that we are not alone. Until then, we wait, we calculate, we refine. We point our telescopes again and again at a star that has burned for billions of years, indifferent to our curiosity. Somewhere in that system, there may be a gas giant swinging along a stretched orbit, or there may be nothing at all. But either way, the search continues. And because this is not just about one flickering point of light, it is about proximity, about destiny, about the fact that for the first time in history, humanity is close enough to another solar system to touch it, at least with light. If S1 comes back, it will not just be a confirmation of a planet. It will be confirmation that we are entering a new era, an era where neighboring stars are no longer abstractions, where exoplanets are not distant curiosities, and where the line between astronomy and exploration begins to blur. And if it does not come back, then we learn, we adjust, and we look again, because that is what we do. 4 light-years away, Alpha Centauri A continues its quiet fusion. Photons leave its surface, cross interstellar space, reach Earth in just over 4 years. And tonight, if you stand beneath the southern sky, you can see that light with your own eyes, unremarkable, steady, silent, but possibly harboring worlds that appeared once in our instruments, worlds that may yet return. The story is not finished. The countdown has begun. And somewhere between glare and gravity, the truth is waiting. Good night. Keep watching the stars, because the next chapter may arrive sooner than we think.